to our next episode about magnetic effect of electric current. In our previous class, we discussed about how magnetic field is produced in a current carrying straight conductor. That means magnetic field produced around a straight conductor. We know this is a straight conductor. If this is the direction of current, then the direction of magnetic field is in it. We can find out by using a right hand rule, right hand grip rule. That means when we hold this conductor with our right hand in this way, if this thumb points the direction of current, then the fingers encircling shows the direction of magnetic field. So the direction of magnetic field is like this. See, it forms concentric circles. Concentric circles. And the strength of the field is, we know, inversely proportional. So the circular ring becomes larger and larger as we move away from the conductor. That means the magnetic field strength is decreasing. So magnetic field is inversely proportional to the distance. Here we want to discuss about magnetic field produced when current flows through a circular loop. We can take this straight conductor, and when we bend in this way, we get a circular loop. What we get a circular loop, and we know that means magnetic field is inversely proportional to the distance. So as the distance increases, field strength gradually decrease. So the circular rings, that means concentric circles, its curvature gradually, that means decreases. That means this becomes larger and larger. That means the concentric circles becomes larger and larger. Here you see, when the current flows through this wall, this circular rings, that means concentric rings, its size gradually increases, and at its center it becomes a straight line. That means we know from every point magnetic field is produced when current flows through this loop. When current flows through this loop, every point of this conductor produces magnetic field. So here also magnetic field is producing, and these concentric circles gradually increases, and at the center this becomes what is a straight line. At the center of the circle, this, that is magnetic field that becomes a straight and is perpendicular to this loop. If there are n turns in this loop, suppose if there are n turns in the loop, then the magnetic field produced becomes n times as that of a single loop. If there are n turns in this circular loop, then the magnetic field produced by this become n times as that of a single loop. Because by using a right hand rule, we know magnetic field is in the same direction in this order. That means current through each of these loop, when we consider that all in the same direction, so the magnetic field also in the same direction. Hence, if there are n times, then the magnetic field produced by this circular loop becomes n times as that of a single coil or single loop. Here once more, what is the nature of magnetic field produced by a circular loop? What are the things you want to remember? One thing that is magnetic field strength is inversely proportional to the distance. So, what happened to the nature of the concentric circles? The size of the concentric circles increase as we move away from the conductor. So, what happens? The magnetic field lines at the center of this circular loop, it become a straight line. It is due to the magnetic field due to this every point in this circular loop. One more thing you want to remember: if there are n turns in this circular loop, the total magnetic field here it becomes n times as that of a single loop, because current in all these are in the same direction. In this all, that means turns. The current in all the turns are in the same direction. So the magnetic field produced by them, we can add it up. So the magnetic field produced by it, we can add it up. So the magnetic field becomes n times as that produced by a single loop. Now, this we can find out by using an activity by connecting this, that means this circular loop that pass through a cardboard. That means in a cardboard, make 2 holes, and if we pass these circular coils through that holes, and it is connected to what is a battery and a plug key. Then after spraying iron dust over this cardboard and plug is on, then we tap, what we can see, this magnetic field here produced forms in the form of concentric circles, and at its center it become a straight line, and its center it becomes a straight line that we can find out by doing this activity. Here, what are the things we want to do? We require a cardboard with 2 holes. Through that holes, the circular coil will pass, and one end of it is connected to a battery, then plug a key, and then connect it to the other end. Then after sprinkler by using what is a salt sprinklers, sprinkle some iron dust over this cardboard, and then passes current through this coil, then tap 2-3 times to this cardboard. Then you can see the arrangement of this iron dust in this cardboard as that of in the form of a circular concentric rings. Now we want to know about how the magnetic field produced by a solenoid. A solenoid is a coil of insulated copper wire wound closely in the shape of a cylinder, that is in this manner. This is an insulated copper wire and it is wounded or wrapped closely in the shape of a cylinder. Then it is connected to with a battery plug key in this manner. Then current passes through this one. We know how the magnetic field lies in a bar magnet. In a bar magnet there are two poles, one north and the other is south. In a bar magnet, magnetic field lines originate from north and it goes to south. That is outside. And inside means its arrow mark towards in. Then inside from where south to north. This is the magnetic field produced by a bar magnet. It originates from north and that goes to south, and from south it goes to north inside. This magnetic field lines, when we observe, here also we get it in the same manner. Here also we get it in the same manner. Here the magnetic field lines, suppose it is, if the current here is clockwise, that is a current flowing in this manner clockwise, and here it is in anti-clockwise. If the current here is clockwise, then it is what? It is the south pole, and one end of this becomes south pole and this end become north pole. Here the magnetic field line starts from, where? North, and it goes to south. When we observe the magnetic field lines around a solenoid, it is similar to that of a bar magnet. So, the magnetic field produced by a solenoid is similar to that of a bar magnet. Here also, two poles, one end is south and other end is north. How we can find out the north and south of this one? See, if the current in this end of the solenoid, if the current is in clockwise direction, see, current is in the clockwise direction, then that end is south. If the current, when we face the end of the solenoid, if the current at that end is in clockwise, then that end becomes south. And when we facing on end of the solenoid, if the current is in anti-clockwise, see, if the current is in anti-clockwise, like this, it is north pole. In this way, we can find the magnetic poles at the ends of the solenoid. That means the end at which current flows in clockwise, that end is south and other end is north. If the current at one end of the solenoid is in the anti-clockwise, then that end is north pole. In that way we can find out north and south poles of a solenoid. We know current carrying solenoid and bar magnet, the magnetic field when we compare, they are similar. Here the magnetic field lines originate from north and goes to south. Inside this one, see, inside this one, these magnetic field lines inside the solenoid, magnetic field lines are parallel. That means inside the solenoid, magnetic field lines are parallel. That means the magnetic field is uniform. Magnetic field is uniform within the solenoid. That means inside of the solenoid, magnetic field lines are parallel. This means here the magnetic field is uniform. Uniform magnetic field is produced here. So, if we place a magnetic material within the solenoid, that means if we place a soft iron is a magnetic material. What is actually magnetic material? A material which can be magnetized in the presence of a magnetic field. A material that can magnetize in the presence of a magnetic field is a magnetic material. Magnetic material. Here you see soft iron. Soft iron is a magnetic material. So when we place a soft iron inside the solenoid, that become a very strong magnet. And now it become an electromagnet. Here you see what are the things you want to remember about magnetic field produced by a solenoid. First of all, magnetic field produced by a solenoid is similar to that of a bar magnet. Hence, one end of it becomes south and the other end becomes north. How we can find north and south poles of a solenoid? To find a south pole, face one end of the solenoid. If the current in that end is in clockwise, then that is south pole. That is just like this, yes, south pole. If the current is in orange, is anti-clockwise, that is north pole. In this way, we can find out magnetic field, magnetic poles. And what about the nature of magnetic field inside the solenoid? Inside the solenoid, the field lines are parallel. Inside the solenoid, the field lines are parallel. So, inside the solenoid, the field lines are parallel. So, the magnetic field inside the solenoid is uniform. Magnetic field inside the solenoid is uniform. Now, here we can find out north, south. Here, what is the property of soft iron? It is a magnetic material, so it becomes a strong magnet. This is the way we make what? This is the way we make an electromagnet. So, how to make an electromagnet means in this method we can make an electromagnet. Now here some questions related to this is given. Let us answer for it. The first question here given is, consider a circular loop of wire line in the plane of the table. Let the current passes through loop clockwise. Consider a circular loop of wire line in this way on the plane of the table. Let the current passes through the loop in clockwise. How it is passing? Clockwise. Apply the right hand rule to find out the direction in which the magnetic, that means apply the right hand rule to find out the direction of the magnetic field inside and outside the loop. That means suppose this is the circular loop. See, current is lying there. So current is hence when we held that circular loop in this way, see, current within this, that means it goes up. That means outside it will be upward and inside it will be downward. What is the direction of magnetic field? Outside the coil it will be in the upward direction and downside it will be in the, that means inside it will be in the downward, in this manner. Suppose we held that one is in this way, then you see finger outside it is going up and encircling this one it will come inside. So outside by using this it goes upward and inside it is downward. Now another question here given, the magnetic field in a given region is uniform. Draw the diagram to represent it. Magnetic field is uniform means the field lines are parallel. Field lines, how it become? That we say if the magnetic field is uniform, the field lines are parallel. Then only it becomes what is a uniform magnetic field. Then next question, question number 3 from page 230. Choose the correct option. The magnetic field inside a long straight solenoid carrying current is, suppose a long straight solenoid carrying current. Here 4 option is given. The magnetic field inside a long straight solenoid carrying current, we know inside a long straight or inside a solenoid magnetic field lines are parallel. Magnetic field lines are parallel and same. That means uniform. So here answer is D, that is the same at all points because it is uniform, hence magnetic field is same. So its answer is D. Now we want to find out magnetic field on a current carrying conductor. Placed in that means a current carrying conductor, when we placed in a magnetic field, what happens to it? See, here is a horseshoe magnet and this is an aluminum rod of about 5 cm length and it is suspended between this north and south, and this is suspended by means of a very thin wire, and it is connected to what is a battery. Plug key, this one. This point is A, this is B. What happens to, let me say here, this conductor is in a magnetic field, and within the poles of a horseshoe magnetic, this is north and this one is a south. Now see, when current passes through this one, what we observe, if the current is passing from B to A by closing the plug key, then we can say this end is moving to what is to the left of this one, and if current, that is by reversing this battery, that means here negative in this way. Now current is from A to B. Now current is A to B. See, in which direction this one is moving. That means by, see, current is in this direction. See, current is in this direction, magnetic field is in the upward direction, and this one is moving in the right. That is, if the current is moving from A to B, then this aluminum rod which is placed in the magnetic field that move to what is right. And if the current is from B to A, it moves to what is left. This shows that a current carrying conductor, when it is placed in a magnetic field, that will experience a force. A current carrying conductor that is placed in a magnetic field, that will experience a force, and hence that conductor moves. This was first observed by Maxwell. That means Maxwell observed that if a current carrying conductor can experience or exert a force on the magnet, then the magnet can exert a force on the current carrying conductor. This was noticed by Maxwell. And here, for our activity, what are the things we took? Here we took that is an aluminum rod which is placed between the magnetic poles of a horseshoe magnet, and it is suspended by means of very light conducting wires and connected to battery and plug key. When we switch on, if the current is from B to A, then the rod is moving to or reflecting to what is left, and if the current is from A to B, and if the current is from A to B, then that one is moving to right. This shows a current carrying conductor placed in a magnetic field that will experience a force, and this directional force we can find out by using Fleming's left hand rule. What we can use? Fleming's left hand rule. That means in the left hand, this forefinger, middle finger and thumb held in mutually perpendicular direction. If the middle finger shows direction of current, forefinger represents direction of magnetic field, then the thumb shows the direction of force or direction of motion of the conductor. By using Fleming's left hand rule, we can find out the direction of force acting in this conductor. Direction of force acting in this conductor we can find out by using Fleming's left hand rule. Okay. Today we discussed about how current carrying conductor placed in a or kept in a magnetic field behaves. How it behaves? That means there is a force acting on it so that the current carrying conductor moves or deflect in the direction of force. That moves or deflected in the direction of force. That means this is actually the working principle of electric motor. This is the working principle of electric motor that we make use in what is in mixing and electric motor and also in computer, where whenever in which places the motor that works in, that is or by means of electricity, there we use this principle, which is the principle: a current carrying conductor placed in a magnetic field can experience a force or will experience a force, and that conductor moves in the direction of force. Okay children, we discussed today about what is the nature of magnetic field in a current carrying circular loop, and how the magnetic field at its center. If that circular loop contains n turns, then what happens to the magnetic field of it? That means it becomes n times. Then we discuss about the solenoid. Actually, what is solenoid? Insulated copper wire wrapped closely in the shape of a cylinder. It is called insulated copper wire or conductive wire wrapped in the shape of a cylinder is called a solenoid. And when current passes through the solenoid, it behaves like a bar magnet, and its one end becomes north and the other end becomes south. And inside it, the magnetic field is uniform because magnetic field lines are parallel. Then we discuss about the principle of, that is the principle of motor. Then we discuss about the working principle of motor, that is a current carrying conductor. When it is placed in a magnetic field, a force acts on it, so the conductor moves in the direction of that force. With this all, we can wind up this class. Okay.